Hey guys, this video is basically kind of a breakdown of what science is, and I was using another video of a guy who I thought did a really good job of explaining this, because it's kind of hard to come up with a definition of what science is, because we use it and see it and interact with it almost every day, so it can be kind of this intuitive process. And so that the guy in the video kind of explained it pretty succinctly, and then I used his video and it got taken down, so it disappeared, and then I never wrote the definition down so that he used in his video, so I had to kind of rebuild my own, and I think I've settled in on a place after watching a couple different videos of kind of a good definition of what science is. So I'm going to walk you through that, and we'll kind of see what it looks like. So first is, I got this flow chart, right? And so I'm going to walk you through this, and then I'll read to you what's going on here. But basically, you have the natural world, and then you have observation and experimentation with a human element involved, and that is kind of the what. It's what you're looking for. And then that gives you evidence and data, which then you can use to predict and explain, in order to give you basically knowledge and understanding. So science ultimately is creating this knowledge and understanding of the natural world by getting evidence or data. Now, there's some issues with things. It's a human quest. Meaning that there can be, humans aren't perfect, so we can mess things up. And then there's also this repeat, reevaluate piece here of repeatability. So my definition, if we kind of follow this flow chart and then kind of narrow it down, science is the human quest to develop knowledge by repeatedly collecting and evaluating evidence through observation in order to come to a better understanding of the natural world. Okay, so let's kind of run through this, all of those bold words. We're going to kind of break down and talk about what they mean, and then this flowchart will kind of travel with us. So the first thing we want to look at is the human element. Okay, so humans have problems. They bring all sorts of baggage to science that we don't really want to bring into the science. Sometimes they bring misconceptions or ideas that they think are true, but really they're not, and so they have these leanings towards certain outcomes, which is called bias. So notice here that humans can bring all sorts of issues to the table: political, geographic, social, philosophical, which is kind of where religion and politics would kind of jump in there, and then when humans introduce their own personal issues along the lines of political, philosophical, those types of things, that is going to be called bias. That can just be one of the limitations to science. Some others that you might think of would be money, time, competition, and technology. So for example, if we're talking in terms of, say, COVID, if you have labs competing to find what vaccine could help us fight off the virus, obviously there's going to be a lot of money involved in that process, and whoever gets to the vaccine first will stand to probably make a lot of money. So the competition there that is driven by money can then be a limitation to science, because you might not be willing to share the evidence and data that you find, which then doesn't build into kind of the community knowledge base, as it were, that helps us kind of solve problems faster. So we'll talk a little bit about that kind of in just a minute, but also notice that those same limitations can also be things that are used to advance science, right? So money can help science, competition can help science, obviously technology can help science. Competition wise, you might think, well, how does that help? There's actually some competitions out there where the first people that arrive at something win a prize. So it kind of drives the research that people are competing for that. Now, it can kind of be double-edged there. Within the competition, there might be other limiting competition because you don't want to share with other people, but the competition itself is driving the science forward. Really what it boils down to this is that good science is objective. That means that if you are a scientist and you are trying to figure something out, it's okay to be wrong, and you got to be okay with being wrong, because being wrong usually just raises more questions, and then you can use those questions to figure out or to build your knowledge base. So if we look up here, notice I have the what and the why here, right? So humans, they're responsible for kind of finding the what and creating the why. So if you are leaning towards what you want something to be, you might make the what come out to where the why is what you thought the why should be in the first place, and that could cause problems. So you need to be objective, you need to be an open-minded person, and you need to be willing to be okay with the what taking you into a why direction that you're not really comfortable with, if that makes sense. So leave your opinions and your non-testable ideas at home. They're not needed in science. So let's keep moving through here and break the rest of this down. First, it's the natural world. Okay, a lot of people get hung up in this. It's science deals with the natural world and natural phenomena. So what is the natural world? It's basically everything that's around you: the air you breathe, the ground you walk on, the visible, tangible things, the things that you can experience with your five senses: taste, touch, smell, sight, sound, right? And if you can taste it, touch it, see it, smell it, hear it, feel it, then it's probably part of the natural world. Now, you got to be careful on that feeling, because we're talking about actually tangibly touching, right? So the feel, like, it's not a gut feeling. The gut feeling is getting back to human. It's getting back to philosophical, and therefore it does not belong in the natural world. You also have to be careful because your senses can trick you sometimes. Our eyes, for example, and our brains, for example, sometimes see things that just aren't there. Many of us have had issues where, maybe you're low on sleep and you see something out of the corner of your eye and you turn and it's not there, right? So you can't always trust your senses, and that's kind of also where this whole repeatable piece comes into play. If I think I see an apparition and someone is standing next to me, or say 3 or 4 people are standing next to me and they don't see the same apparition, then we can't say that apparition exists, and that apparition then is not of the natural world until we gain more evidence that might suggest that. So notice that the natural world is those tangible things that we can observe and gain data on. So what is it not? The things that most humans classify as supernatural or religious. So let's take aliens, for example. Can we prove that they were here? No. Are there people working to prove that they were here? Sure. If an alien shows up and thousands of people see the alien and talk to the alien, can we now say that aliens exist? Probably so, right? So then they cross from supernatural into the natural world. So notice that just because something is supernatural or religious doesn't mean that you can't scientifically explore that. It's just that sometimes the evidence has to mount up enough to where you can actually support that as being something that is then part of the natural world. So as of right now, there are no scientific ways to explain, or no scientific data to explain some of those things. Did they happen? Maybe. Can we prove it? Not with tangible evidence and data as of yet. Are there people looking for it? Sure. And is that okay? Yeah. So notice that it's got to be reliable evidence that builds up over repeated experiments. So let's look at evidence then, because evidence is probably the most important part of this whole science thing. So what is evidence? Evidence is basically going to be obtained through careful, controlled observation and experimentation. So whenever you are doing an experiment, you are trying to gain observations, right? You are trying to gain data. So an observation is where you use your senses to gather information about a particular phenomenon in the natural world, right? So using your senses, smell, sight, taste, touch, and sound, you should be able to gather that evidence, and then we're going to do something with it. So notice here, this is pretty important. Technology then is going to be anything that can enhance your ability to collect observations or to collect data. So for example, if I'm like, we didn't know that a cell existed, right? There was thought that, you know, your skin is made up of smaller particles that, you know, do perform functions, but we didn't know exactly what those were. We just had this feeling that they were there, and, you know, your skin looks different than other things, so you know, there has to be a reason for that, and so then their cell theory came along, and we basically were saying that things are composed of tiny little compartments that kind of work together to do specific tasks. And so some of the technology that helped us is obviously with your eye, you can't see necessarily the individual cells, but with the invention of the microscope, we can then actually look closer and see cells, and then within the cells you can see organelles performing little tasks for the cell. So technology basically is something that enhances your ability to use your senses to pick up on those observations or that data. So the experiment piece of that, so observation is kind of the data. The experiment is how you get that data, right? So it's where you control the conditions, and you decide, you can manipulate variables, and you can add things and take things out to figure out what is going on. So notice that is the what piece. So observation and experimentation helps you determine what the evidence is about that natural phenomenon, which is really important, because once you get all of that evidence, then you can start to break that evidence down. So let's talk a little bit about evidence in the form of data. Okay, so data can be quantitative and data can be qualitative. Quantity means that it's a number, and then we also need a unit, because I would not say I am 5, because you could then say 5 years old, 5 feet tall, 5 feet from the moon, 5, I mean, what is the 5? So we have to kind of quantify and qualify what that 5 means by giving it a unit, right? So quantitative data is a number and a unit. It tells us exactly how many of something we have, right? And then qualitative is going to be descriptive or explanatory data. So the beaker got hot when we added something to it, right? That may not be a number, but it gives us some evidence that could paint a broader picture of what's going on, or might have more what questions, right? Or might be why does that happen, which leads to more what. So qualitative data then is going to be kind of that descriptive data. What are you seeing, feeling, those types of things. Then notice this, good data is repeatable, good data is factual, and then quantitative data is usually more powerful from a scientific standpoint. If I have numbers tell me things, and they give me more factual data. It's less likely for me to introduce my social, political, religious biases when I'm using numbers. When I use qualitative descriptors, oh, he was a nice gentleman. Well, nice is not an objective term, right? I might think one thing is nice, someone else might think that that's totally rude, right? So qualitative data then isn't as powerful, but we can make it more powerful by quantifying it. So, for example, if someone eats Frosted Flakes and says, "Man, Frosted Flakes are delicious," you may not agree with that from your political background or your religious background or your whatever background. You may not agree with that. So that is not a fact. That's an opinion, right? If we wanted to say the majority of human beings like Frosted Flakes, well, now we could quantify the data. So we could go around and survey all of the people and figure out how many people on average like Frosted Flakes. So if we go and we find 100 people and we ask them, what do you think of Frosted Flakes? And they say, oh man, I love Frosted Flakes, right? If I get 99 people saying that I love Frosted Flakes and you're the one holdout that does not love Frosted Flakes, then we're basically sitting in a position where we can say 99 out of 100 people, or 99% of the people, prefer or like Frosted Flakes. So we've basically quantified the data. We've said that 99% of the people, number, unit, quantified, makes it more powerful, makes it a little bit more factual, even though it's not true in all cases, it is true in most cases. So it gives it some statistical power, basically. Whenever possible, qualitative should be quantified. Good evidence also helps us explain and predict what happens in the natural world, which is getting to the why phase, right? So why do we predict and explain things? Because that's going to give us the knowledge, and we can take that knowledge and turn it into some understanding. So let's look at that. So knowledge is basically just the information. It is a body of evidence. It is the factual information gathered from experiences. So remember, humans are gathering that information, so biases can lead to a debate about what's fact and what's fiction. So sometimes we have to use more science to try and wade through that. But for the most part, factual information is things that we can see, that we know are happening, and we can essentially prove that they are taking place, right? So it's a body of evidence. If we find that this happens and it happens and it happens and it happens and it happens, then we got to be pretty sure that that's factual information. So it's kind of reliable. Understanding is a little bit different than knowledge. Understanding is actually taking what you know and organizing that so that you can actually use it or apply it to similar circumstances or similar sets of knowledge. So basically, knowledge comes first. You got to have some data, and then understanding comes after that. How do you apply that data, right? And then if you want to get into kind of the philosophical realm, there's a thing called wisdom that is kind of where we leave the road, and it's how do you apply your understanding in light of what you know to be right or wrong. So that right and wrong then becomes objective, so we wouldn't really want to talk about wisdom, but I wanted to throw some philosophy at you. So anyway, if we keep moving on, if we know that knowledge is the information base and then understanding is how we apply that to maybe new ideas or concepts, or even reorder some of that knowledge to create a better understanding, then we can kind of move on. So why do we repeat, evaluate, and then reevaluate? Mainly because repeatability means reliability, which reliability gets us as close to fact as we can get, from being fallible human beings. And then repeatability of the factual is probably going to be a law, and I'll show you kind of where that fits later. And then reliability of factual information is probably going to be a theory. So if you can repeat, evaluate, find new evidence, Your body of knowledge then grows, changes, and then you might need to readjust your understanding, which then might lead to further adjustments of how you understood a different body of knowledge. So we always repeat, evaluate, and then reevaluate, because it basically makes the entire process and evidence that we found more reliable, more accurate, more dependable, as it were. So let's look real quick at law versus theory, and then we'll kind of put a cap on this and move on. I stole this from a guy on YouTube. I like what he said about this, and I think it kind of makes sense. So notice, let's look at this. So the natural world gives us, something that we want to figure out. So we have to figure out the what. So we observe and we experiment, and then that gives us the what, which is kind of the data, right? The evidence. But then we've got to take that evidence and we've got to construct it or order it so that we can explain or predict why what happened, or why what happens. So maybe kind of the easiest way to look at this is, everybody says Isaac Newton discovered gravity. Well, gravity's always existed. He didn't discover it. He basically developed the idea of what gravity was. So basically we have an apple supposedly fell and hit him in the head while he was under a tree or whatever, and he was like, well, why do apples fall off trees? So in order to figure out what is causing the apple to fall to the earth, he had to start to develop experiments or observations, which then gave him more evidence or data. So the first thing that he probably noticed was that all apples fall off of the tree at some point and hit the earth, unless obviously someone picks it and eats it, and then it never has a chance to hit the earth. But he's basically finding evidence and data that is starting to develop kind of a knowledge and understanding. So he gets to a point where he says, well, all apples fall from trees and hit the earth. So then what is causing the apple to fall and hit the earth? And now that could be thousands of other questions, right? But the fact is that the apples fall and hit the earth. So notice that if we're observing a single event and we have that observation, that single event, the apple falls from the tree, that is a fact, irrefutable. Did the apple fall from the tree? Yes, I saw it. Did another apple fall from the tree? Sure, I can see that too. So those are facts. So every apple falls from the tree. That is a fact, right? Now, that is building up our knowledge base. But we aren't to the point yet where we can explain it. We kind of have to predict, why is the apple falling off the tree? And some people thought, well, maybe it's falling off the tree because it loves the earth and wants to be close to the earth, right? And that's probably getting into some feeling and emotional things that we want to keep out of science. But the idea is we're predicting some things, and then that makes us go back, and now we can set up more controlled experiments to figure out, why is the apple falling, and basically we keep kind of evaluating and repeating, right? And we get to the point where at some point, let me talk about that first. So we're trying to explain that single event, right? And so we develop hypotheses that can explain that single event. Then we can set up a test that then will give us more data that will explain away that hypothesis. And if we can explain away that hypothesis, we can get rid of that idea and we can find a new prediction about what could be causing it. But if we can't explain away that hypothesis, well, now that adds to our knowledge base. That tells us that something is there and we need to investigate it further. So a hypothesis then, notice, is basically a prediction about the natural world that we could collect some evidence on that would then allow us to understand something better, right? So a lot of people will say that a hypothesis is just an educated guess about something. Well, it's a little bit more than that. You have to be able to set up an experiment about it that collects evidence about it that hopefully gives you more knowledge about the subject, and then helps you rearrange your understanding of it. Otherwise, it's actually something that is it's beneficial either way, but it's actually something that we will then throw out, right? So we're trying to disprove that hypothesis, and if we can't disprove it, then we have to maybe accept it or find other things that could then disprove it. However, you would basically be doing repeat, evaluate, whatever, right? So if we get that, right, if we look at an observation though, and it is true for all events, so now if we talk about, well, apples fall to the earth, but then so do a bunch of other things. Well, what Newton came along and found out was that gravitational bodies exert gravitational forces on each other, so they're attracting each other to each other, and therefore there is a gravitational force between two objects that actually draws them. So like the moon is pulling on the earth is pulling on the moon, and someday the moon could eventually fall into the earth, or if you want to look at it the other way, the earth could fall into the moon, but usually the smaller body is falling into the larger body, as from our observation point. Anyway, gravitational force then becomes a law because it applies to all objects, and usually those laws have mathematically driven explanations, if that makes sense. So you can usually say that those laws that really always are at play, there is some sort of mathematical representation that keeps those. So a lot of those, like Newton's laws, are the easiest ones to see. If you add an outside force to an object, that object will move, and you can see that in force equals mass times acceleration, right? There's acceleration is whatever, right? But so there's mathematical explanations to laws, right? Theories then are kind of a little bit different. So notice that fact and law is kind of the what, right? If it's a single event and you're observing that single event, what are you observing is a fact, right? And then if it happens for everything, what you're observing is a law, right? So explanations then kind of are a little bit different. A hypothesis is where we want to explain, the events that are happening. So if we take a single event and we try to explain it, we can then do the test and observe about it and figure out, well, that does or doesn't happen. If it happens, if our hypothesis holds true for a lot of events, and we start to see a pattern emerging of oh, that works, oh, that works, oh, that works, then we start to develop a theory. And that theory is basically a broad explanation of evidence, right, that expands our knowledge and understanding. Can it change? Yes. So can we change a theory? Yes, because if we find new evidence or data that suggests we need to tweak that theory or change the understanding of that theory, then we would need to do that. Laws typically, they might change a little bit, but for the most part, those are just like physics governing the natural world. Like, they're just the way that they are, and they're not going to change. So it's kind of hard to wrap your head around that sometimes. So really, if you kind of think of it in that terms of what and why, a what you can't really explain away. If you see it happen, it happened. If multiple people have witnessed that it happens, it happens. And then if you can't change the fact that it's going to happen, then it's going to be a law, right? But then the whys, where people kind of try to explain all of this stuff, sometimes can have some issues, and sometimes we don't have the full body of knowledge to be able to say that this is what always happens. So we're working off of theories. And so we hypothesize that this happened because, and then we can set up an experiment, and if this happened because, then we can get other people to repeat that, and then it becomes a repeatable event that occurs over and over, and we could say that it's theory, or we get subtle changes within it. But notice that things can change. Science is not set in stone. We can, as long as we find new evidence and data, then we are going to constantly have to be changing our knowledge and understanding, right? Does that change the natural world? No. The natural world is still going to be the natural world. It just changes our understanding of how we interpret the evidence and data that we find in the natural world, if that makes sense. So, recap, science is a mess. It's a beautiful mess, but it is a crazy mess, and when you throw humans into it, it becomes even messier. So it's kind of hard to define. So let's go back to it and just kind of see what that definition was. It's a human quest to develop knowledge by repeatedly collecting and evaluating evidence through observation in order to come to a better understanding of the natural world. So really, if we wanted to even boil that down further, it's the controlled process of understanding or gaining a better understanding of our natural world. So we're going from natural world to understanding, and the way we get there is with some evidence, right? How do we get that evidence? We experiment, we make observations, and then we take that evidence and we basically explain the why that happened, if that makes sense. So hopefully I've thoroughly confused you, but enlightened you, and then hopefully your understanding of the knowledge that I've given you has become a little bit more clear, though it was a convoluted sort of journey to get here. So natural world, evidence, knowledge, and understanding, that's what science is trying to go towards, and it needs to be able to be repeated, evaluated, reevaluated. Otherwise, it's not science.